Okay, so why are we doing PDEs? Well, turns out that most problems in engineering have to do with PDEs, like heat conduction equation, Navier-Stokes equation, fluid mechanics, heat transfer, dynamics, vibrations, to some extent, will have PDEs. Okay, so the last homework will be on PDEs. Okay, and since you came for the class and people were on Zoom, here's a bonus. I did not want to announce this before the third exam, but I will have a fourth exam where if you answer the fourth exam based on PDEs, I'll swap it with the worst exam. So if you have, usually first exam was, many people did not do well. So I'll replace that fourth exam with your worst exam. So it'll be the first exam, second, third, whichever. Okay. So study this. This could change your grade by a whole lot. And that's not mandatory. You don't have to do the fourth exam. It's up to you. And we'll have it approximately 2 weeks from November 6th. So November 22nd, I think. Yeah, so we should be done with PDEs maybe next week, and then we don't have to actually meet. Your project is almost done. I've working on it, but for the project, you only need to know stuff till ODEs. So last thing is shooting method. You don't really need to know up to ODEs. So PDE is not going to be part of your project, but I'll post the project. Give me a week. I don't think anybody is going to do the project till November 6th because you have an exam. So I'll post the project November 6th and give you a whole month, December 6th, to complete it. December 6th is the last day of class. So I know I overloaded you in the first half of the course. That is to make your life easy now. So now it's going to be fairly easy. Okay. Okay, so let's start with PDE. I'll just introduce it and then I'll let you go. We have 6 minutes. So equations for PDEs are something like this. Okay, so you see that there's an x and y, and there are partial derivatives. Unlike ODEs, where there was a complete derivative, right? So the partial derivative is important. Basically, it is if you think of x and y as if you think of a heat conduction, then x and y could be the boundaries of a plate. Navier-Stokes, again, you could have x, y, z, where it could be the fluid flowing in x, y, z direction, and so on. So there's a way to classify these equations, and the methods depends on how you classify this equation. If b square minus 4ac is less than 0, it's an elliptic equation. If b square minus 4ac is equal to 0, it's a parabolic equation. And then if b square minus 4ac is greater than 0, we have a hyperbolic equation. Or whether maybe the best way to cite this is PDE, not equation, PDE. Okay, unless you know this first step, it's very difficult for you to apply any method. So you better know this classification because the methods depend on which one it is. So I'll give you some examples of either of them and I'll let you go. So here are some examples. Heat conduction. This is a parabolic PD. Okay, I want you to check this out. Here, what happens is B is 0. So if you compare against this equation, you can make out what the equation looks. So A would be 1, B would be 0, C would be 0. So A is 1, C equal to 0. So when you do B square minus 4AC, you get 0. And that's basically makes it a parabolic PDE, right? Is that right? Parabolic PDE, that one. Okay, you might have seen this equation in your class. I'll just write two more and let you go. So the other one is Poisson's equation. This equation looks like this: t square phi dx square plus t square phi dy square equals beta xy b square minus 4ac. So here b is 0 because that's the cross term, x and y, minus 4 times ac, which is less than 0. So it is an elliptic PDE. And then finally, wave equation. Which looks like this: t square phi dt square minus c square d square phi dx square equal to 0. Here we have b square minus 4ac. So b is 0. 4a is this coefficient, it's 1. C is basically this minus c square. So you see that this term is greater than 0. So it's a hyperbolic equation.